My name is Avi Alkobi. I'm a technical marketing manager in Mellanox Technology. How many of you guys are familiar with Mellanox? If you can raise your hand, except of Mellanox employees. Okay. Yeah, so it's pretty good. Okay. So Mellanox is basically started as an InfiniBand company working for the HPC industry. We're building our own silicons. We started in InfiniBand with our own silicons. We're specialized in high-performance computing. It means that we know exactly what to do to provide high bandwidth, low latency, those kind of stuff. And then we moved forward, I think it was 6-7 years ago, we moved forward to the Ethernet world, and now we are basically providing the qualities of high performance. It means high bandwidth, low latency, non-blocking network, also to the Ethernet industry. And in this session, 30 minutes, I'm going to talk a bit about the acceleration and performance and offloads capability that we are offering as part of the OpenStack cloud, the modern OpenStack cloud, and how exactly we are trying at least to reduce the complexity. So let's start from the end. And the end basically says that today in our industry, we have a few demands. And our first demand, the biggest one, is that we have data explosion, right? It's not a secret. Everybody, one of us is just playing with our iPhone, taking as many pictures as we want, post them on Facebook, other social media frameworks, as much as we can. Okay, we're doing it all the time. So we have a lot of data running, and storage devices are getting much faster. So just for you to understand the ratios, to make a 100 gig link be really fulfilled with spinning disk, you need I think 240 spinning disk to run 100 gig. Today with NVMe, if you have 4 NVMEs, you are blocking your network. You need at least 100 gig. So we would like to have storage that is more efficient. This is number one. So we have here a number that we can say that we can do with our offloads capability, 6. We need also, usually, when we are talking about cloud today, we're talking some kind of an SDN solution. Sometimes, and most of the times, we're talking about overlay networks. The problem with overlay is that traditional network really doesn't know how to handle it. If you are putting a traditional NIC to your network, and it's just a packet of VXLAN is coming to it, he's just looking at it and saying, I have no idea what to do with it. So what he does with it is just pushing up to the software to handle it. And we'll talk a bit about it. So once you are pushing stuff from network to the software, it means you are slowing down your bandwidth. And those capabilities that we're offering as part of the overlay offloads, I will talk about them a bit later, are also essential to keep up with the speeds that we need in our cloud. And of course, latency is also essential. We're coming with, as I said, with latency from the HPC world, and we are also offering it as part of our Ethernet portfolio. So we are, basically I'm talking here about Mellanox adding features that will do offloads and accelerations and all sorts of nice things. But the problem with about OpenStack, it's already very complex, right? It's a very complex thing to raise up an OpenStack cloud environment. So adding more stuff to the table, it means that, making things more complex. So the way not to do it more complex is make sure that you are putting those features and capabilities as an out-of-box experience. It means basically you plug it in and it plays. Okay, this is the way that we would like it to be, right? And the way to make it happen is, first of all, if there is some kind of a configuration that you need to do to make something happen, make it as simple as possible. And the perfect way will be probably to have it in-box. So I'll mention it later on my slides, where exactly we're integrated and from which version in the OpenStack releases. So this is around the server side, and then around the network side, you still have a network that you need to manage. It's part of your cloud. You cannot avoid it. What we would like to have in our network is an option to somehow automate it, orchestrate it with tools that are very easy to handle, or maybe the perfect way, and there is here the logo of Cumulus, maybe the perfect way, maybe I'm not sure, but something that can be a discussion between people, and each one can think differently, but maybe a very good way will be to run Linux on your switch. Once you have this, you can manage your switch the same way that you are managing also your servers. So I will not mention, of course, you have only 30 minutes, all the capabilities that we are offering as part of accelerations. I will mention a couple. And I will start with RDMA. Who is familiar here with RDMA? Can raise his hand. Okay, cool. So RDMA, in the language of Ethernet, it's called RoCE, which is RDMA over Converged Ethernet. And everybody is here. If I will ask who is familiar with TCP/IP, I'm pretty sure everybody knows. So no need to explain that. But again, the usual way that people are working is basically they are using TCP/IP to push traffic from the server out to the network to certain destination to copy memory basically between machines. This is the idea of running traffic eventually, right? And TCP/IP was created, back in the last century, and it was not really built for the speeds and performance that we are asking today. And basically what happens is through the years there are more efficiencies, programs to make it more efficient and so on, but still we are talking about operation which is mainly around networking, right? Pushing traffic on the network that is managed by a stack that is part of the software. RDMA basically says for network operations, you should not use the software, the CPU. The CPU should be used for the application. You should use the power of the CPU for your application, for your services. For the network, what RDMA is saying, we can just take the buffer from the application level and push it directly to the NIC, bypass all the TCP stack, and push it directly to the network. And I will explain how does it work, but the consequences of doing RDMA versus TCP/IP is that you can run 100 gigabit with your server. If the server is powerful enough, if you have the PCI capabilities, you can power it with, run it with 100 gigabit with a very, very weak CPU. How does it work? It works like this. Basically, there is a shared queue between the NIC and the process. The process, of course, has its own registered memory, is using it. And this shared queue pair, or we call it short QPs, is basically, by doing that, is able to access directly to the memory, copy the memory piece that he needs. He's using, of course, the logical address. He's on the NICs level, on the hardware, he can do the mapping between logical and physical. He's pushing the packets, do segmentation and push the packets using another logical address, not the same one as I mentioned before. And then on the other side, the same thing happening again. So there is some kind of a handshake at the beginning that creates this kind of connection between the application and the NIC side. But once the connection is ready, the software is out. For every operation, that means that we need to do I/O, we need to push traffic. Everything is done with the hardware that is coming with the NIC card. And that means eventually that, and this can be shown easily with benchmarks, and there are nice videos on the network that you can also see. With RDMA, basically, you can see high speeds with zero CPU. You need CPU for running traffic. There are different ways to actually create in the application level this mechanism. The most easy, I think, way is using the send receive, the same send receive that we're using when we're doing TCP/IP, using sockets. So for the application level, it's pretty easy to use RDMA. And the advantage of that is eventually I can get numbers like 150 million packets per second. And except of just doing the operation of RDMA, of course, the NIC is taking care of all is related to what was before part of the software job, and it means, for example, to do RSS, and TSS, and other stuff. Now, this is nice. If we agree about RDMA, it's nice. But the problem is, till now, I talked about bare metal or hypervisor level. What about virtualized cloud? This is the interesting part. So let's go back and do some overview about what happened with virtualization and network. So at the beginning, there was a concept that is called virtual interface or emulated device. Basically, it means that the software is emulating the device, the physical device, on the hypervisor level. This is a very easy way to implement a VM interaction with the NIC side. You don't need to install special drivers on the VM. The VM is using the same drivers as used on the kernel. The problems with that is that it's very, very slow. It's fully software managed. And the overhead is very high. Next step was a concept that is called para-virtualization, or PV in short, which basically created a switch-friendly device on the VM. Now we are disconnected from the drivers of the kernel. So the problem with that you need cons that you need to use different drivers for the VM. Still, it's a simple solution. It means that for complex network NIC cards, it's more problematic to implement this kind of solution. The other part, the problem with this solution, there was a bouncing between the VM and the hypervisor while trying to run traffic because there was some kind of a handshake and then going to the kernel and again, then go back to the VM and then going back to the kernel. So there was a CPU running very heavily between on the server side to make it happen. The next stage was an accelerated para-virtual, which is kind of improvement of the PV concept, and other modules on the kernel basically that stops this bouncing process. And the next step was maybe thinking about taking the actual physical driver and just put it on the VM. Okay, so it's a copy of the physical function of the network, just copy to the VM, which is nice, but the biggest problem with that, you cannot, of course, scale, right? Because if you have 2 ports, you have also 2 VMs, something like that. Of course, it's a problem. But the idea was, beginning with that, is that we should find some kind of a way to, again, eliminate the CPU, take it out of the process and making sure we can somehow get a VM direct connection to the physical network. And the last step was a concept that is called SRIOV, which is single root IO virtualization. And this concept means basically that you have the physical function, the actual NIC card connection to the PCI, and we are creating many, many copies of it, which are called virtual functions. And we are just taking those virtual functions and giving them to the VMs that are created on the server side. So now each VM has a virtual function that is actually a direct connection to the NIC card, but there are many of those. We're actually sharing the same physical resource between many VMs. And the pros with that is that there is high scalability. We can create many virtual functions. We're talking about 128, 256 virtual functions. Near native performance, because guess what? Now we can use, for example, RDMA. Okay, so all the concept that I talked before on bare metal of bypassing the TCP stack and going directly to the network, now can happen also in a virtualized environment. The cons with that is that there is no transparent integration, and it's quite a problem. I think it's a problem not only for SRIOV today, but this is something that we are working with the community right now to make some assessment about how we're going to improve that. I think there is kind of a work that we are doing in Okata, towards Okata about this issue. So SRIOV is available. Now, as I said before, we have nice features. How exactly we make sure that they are not getting you or guys that are handling OpenStack Cloud in a place that it's more complex for them to use them. So at the beginning, House, we started with the Mellanox mechanism driver. Mechanism driver, I'm not sure if I need to explain. It's part of a group of drivers that are called modular layer 2 ML2, basically drivers in Neutron, which are drivers that their purpose is basically to provide layer 2 functionality between the neutron and the network. And we supported Mellanox mechanism driver, which we're still not in box. And from this, basically from Icehouse, we were able to create or be able to support this diagram, which means basically that we have our driver in the controller, we have an agent that can control a concept that is called eSwitchD. eSwitchD is basically a daemon in the hardware, in our NIC card, okay? It basically gets the RPC and is able to communicate with the eSwitchD and do the actual configurations. But also, it's backward compatible. So if still you are using OVS mechanism driver, it will work perfectly. It would just go through the agent on a different path. And from Juno, it's actually in box. So it is called SROV NIC switch mechanism driver. We are not the only ones that are doing SROV. We think that we are doing it better because we come with some kind of a knowledge about how to do high performance, but there are other NIC cards that are doing it. So now it's a mechanism driver for those NIC cards. We still kept the Mellanox mechanism driver. We did it mainly because we're still doing InfiniBand, of course, and we wanted to support also InfiniBand. So this was one concept of acceleration. As I said, removing the CPU as a bottleneck. By the way, there is another way to accelerate traffic, and it's not to push the CPU out of this logic, it's putting more CPU, okay? It is called DPDK, if you know what does it mean, but basically it means that if you are putting more CPU power, of course, eventually you will be able to run high bandwidth. You can do that, but the way we think is basically CPU cost is much higher, so you don't need to put much money on the CPU side just to run traffic. You can use the capabilities on the NIC. So we finished about this, and now I'm going to talk a bit about overlay network. So overlay network, and I will talk specifically about VXLAN. This is the most common way to do overlay. In a couple of words, means that we are creating tunnels between hypervisor, and we are leaving the concept of VLAN behind. We're moving to a concept that is called VXLAN, and the main reason that we are doing it is because we need more scale. Okay, so with VLAN we are stuck with 4K VLAN. It's not enough. Okay, we need much more segmentation in our network. So this is the main reason that we are going with VXLAN. But VXLAN means that we are doing packet encapsulation. It means that we are taking the packet, which is a UDP packet, and putting inside another packet. And I will explain why in a couple of words. Basically, when we are doing VXLAN in OpenStack or in other environment, hypervisors are creating tunnels between the hypervisors. The ID is called VNI. It's kind of a replacement of VLAN ID, but basically it's a tunnel between the two hypervisors. And on the hypervisor level, it means that you can have two VMs with the same VLAN or the same IP, but they are on different VNIs. So from the hypervisor side, he needs to know how to map the traffic that is coming from the source to the right VM on his side. The traffic is kind of on a VM level, looks like layer 2. Right, so it's equivalent to VLAN, layer 2, VXLAN, it's layer 2. But on the other layer, you are using layer 3. So all those operations can be done by, of course, ML2 mechanism driver on OpenStack that is creating the configurations on the hypervisors. This is the concept. But as I said, the problem with VXLAN, the main problem is that if you are connecting a traditional card into your server, there is a problem because the traditional card knows how to handle VLAN. It doesn't know how to handle VXLAN. So what will happen is basically he will see UDP packet. He needs to somehow peel those headers and get to this place to make sure that the original MAC number is clear to him, and of course the VLAN. He needs to use this part of the packet to identify which VM needs to be receiving the packet. And it doesn't know how to do it. So the next thing that the NIC will do, the hardware will do, it will push it up to the software. And then we are getting the same discussion again about why using CPU power to do networking. And with VXLAN offload, which is part of the ConnectX 4 cards that we are offering, and ConnectX 3 Pro, the cards with the 1 to 100 gigabit. This is basically what we are doing with our NIC cards and switches. The offload capability is inside the NIC. So basically, the hardware is doing this job. He's able to do the checksum, the RSS, the TSS, the heavy operations that needs to be done in the overlay network. And you can see in this graph, you see the light green one is basically a VLAN. The green one is a VXLAN with offload on the hardware, and the red one is VXLAN without offload. And this graph is about CPU usage. I'm talking here about 40 gigabits, but the same number is also for 100 gigabit. You can see that as long as you are taking more and more VMs, putting them on the server, when it comes to CPU, the CPU kind of stays the same between VLAN and VXLAN, but CPU picks up when there are more and more VLANs, because here, for example, for 16 VMs, the software needs to work hard to do this operation of VXLAN, checksums, and RSS, and other stuff. And on the other side, we see the throughput. Again, this is a 40 gigabit, but the same for 100. You see that the performance is quite close between VLAN and VXLAN with the offloads, but once going without offload, the bandwidth is dropping. And this is the important thing that we need to know about the network. Putting an infrastructure of 25, 100 gig in your network doesn't mean that that network in the pipelines will run 25 or 100 gig. It will not. Because once it will hit the NIC and it doesn't have the offload, the bandwidth will drop. Once the packet will hit a switch, it doesn't have enough power to push it up and maintain the bandwidth will drop. So infrastructure of 100 gigabit is great. We'll show even a slide of real installation of such OpenStack cloud, but you need to use the right features to make it work. Configuration of VXLAN offload, as I said, it's important to keep it simple. It's really on the configuration file of the driver, one parameter. It's kind of almost a default. There is a community around it. You can read about it if you like, but basically you configure one parameter, that's it. The NIC is doing the work of VXLAN offload. This is a roadmap item, but it's very interesting because when talking about overlay, it's not only about checksum and offloads of the VXLAN, it's also about being in an environment when usually you have a controller which is controlling through the OVS DB, the Open vSwitch. It can be a controller or EVPN or other technologies, but eventually there are operations that are done by the OVS. And what we are trying to do, and we'll have something something preliminary in Okata, is basically moving the OVS to the SRV concept. Means that we are going to have some functionality in the switch hardware that will be able to, the controller will be able to directly control it on the hardware, so it will not go to the software. And if talking about the way that it's working, so with OVS, regular OVS, basically there are rules on the application user space and kernel. If the rule is, if you have a match on the kernel, that's good. If not, it will go to the slow path to the application. It will be even slower. What we are going to do is basically create net devices on the eSwitchD and basically be able to configure the rules on the hardware level. So if you have a hit on the hardware level, great. If not, it will go to the kernel. If not, it will go to the user space. The reason that we are keeping the flow like this is because we cannot, at least on the first day, have all the functionality of OVS DB in the NIC, of course. So we'll have the important ones, and you will get the hits there, but if there is something that will not hit there, you are still going to use the same mechanism. So everything is backward compatible, of course. A bit about the physical network and the features that are needed on the switch side. So till now, I've talked about the goodies on the NIC side, the accelerations and offloads and everything. But as I said, a full solution means that you need to take care of the NIC, the switch, also the cables, by the way, are very important. One word about Mellanox, we are doing end-to-end, by the way. We're doing NICs, cables, and switches. We're doing end-to-end also on the vertical level. When we're doing a switch, we're doing our own silicon, our system, and the software inside of it. Why I'm mentioning that is because you don't have to use everything Mellanox or everything Arista or everything other companies. You can choose. But when you have a partner that knows the end-to-end view, sometimes it can help. And basically, what we are saying is that the switch, first of all, needs to be a good switch. You need to maintain the bandwidth. You need to have the functionality of, for example, VTAP on the top of rack level, because sometimes you will need layer 2 gateway on the top of rack because you have a bare metal, for example, so you need to handle this. So you need the features of VTAP, and as I said, a very good switch, high performance switch that is fair, low latency, and so on. And the solution of the software above the switch, it can be Mellanox OS, it can be Cumulus, it can be other stuff. The ability to choose a software that fits your demands is very important. If, for example, you have a team of Linux guys, and they are very powerful with Linux, having Linux on the switch system is great for them. They can use the same modules, Ansible modules or Puppet scripts that he's using on the server, the same one onto the switch. It's very, very powerful. But if your team is kind of more industry-like and network guys that are that are used to CLIs and so on, then you will probably choose an operating system that will fit that, and you will need some solution of software that is controlling the fabric from above. And being able to do it maybe with open APIs like REST APIs, so you can integrate it in your software system. And of course, one more important thing about the network is that you will need integrations with companies like Midakura, Midonet, or VMware NS6, or other solution, SDA solution. We don't have much time left. I will mention in 2 words the concept of switchd. I said that you can run Cumulus Linux as a Linux on the switch. What we are pushing right now, when it's in POC level, it's the basically driver for a switch as you have a driver for a NIC. So if you have a NIC, you are pushing it to the server, installing a driver, you have 2 ports, you can configure it, right? You have ifconfig, everything is there. What we are saying, Mellanox, is that you should, or maybe, do the same with the switch. But instead of seeing 2 ports, you will see 32 ports, right? And you can use the same tools of Linux that you are happy with to control your switch. And you can choose the distribution of the Linux that you would like to use. And you can install the driver. So today we're running Quagga basic layer 2 with Fedora latest. And basically we are showing that we can do that. Okay, we can take a switch from Mellanox, install Linux distribution, put the driver there, and run it. I didn't mention OpenFlow. I mainly touched overlay, but I mentioned that you can have be able to do the choosing between operating system. This is something that we offer, and offering that means that you can also choose your SDN solution. So, for example, Cumulus are more oriented to overlay. They will not do OpenFlow. You can swap to Mellanox OS maybe, if you would like to do OpenFlow. So we have different choices there, and this is available. Just for a summary, I mentioned reduced complexity. It means that basically all the solution needs to be integrated inside inbox level. So I didn't even mention our accelerations when it comes to storage. We have inbox integration on Cinder. When it comes to storage with ICER, we have solution with RDMA. And Ceph, we have NVMe solutions. On the compute server, we talked about RDMA and so on. Neo, the management of the fabric, integrated in Horizon from, I think, Kilo, if I remember correctly. Integration with major distributions, of course, are mandatory as much as inbox as you can. I will finish with this topology. This is a hosting company in Germany. I took this example because they are really doing everything. And basically, they have using VXLAN offload. They are doing rating for OVS offload, running Cumulus all over, and layer 3 from the host to the spine level. I need to finish. I thank you very much for your time. If you have any question, we are in our booth. Thank you.